Okay, this is on locating zeros of a polynomial function. And first let's go back a zero of a function, and they might call it a zero, a root, or a solution. A zero of a function is a value of x for which f of x equals 0. And remember, f of x is the same as y, so it's a value of x where the y value equals 0. Graphically, the 0 of a function is where it crosses the x-axis. This would be a 0, this would be a 0, and this would be a 0. Where it crosses the x-axis. Those are called zeros or roots of the function. Okay, and let's go through a couple of examples. In the directions in the book, it will say find the number of positive, and we're going to abbreviate it. Find the number of positive, negative, 0, and imaginary roots. You can abbreviate it. And the equation is 3x to the 4th minus 8x to the 3rd minus 30x squared plus 72x minus 12 equals 0. Find the number of positive, negative, 0, and imaginary roots. Now, notice in the directions, this is not saying solve the problem. It just wants to know how many times does it cross on the positive end of the x-axis, the negative end of the x-axis, does it ever cross at 0, and the imaginary roots would be where it did not cross the x-axis. So I just want to know how many of those we have. Okay, now we're going to do this a little bit differently than the author. The author sets this up and just does it with, gives your answer with commas. We're going to set it up in a table. And when you do the table, there's always 4 columns. It's always in this order: positive, negative, 0, and imaginary roots. Okay? And to figure this first box, you go back up to your beginning equation and you look for what they call variations in sign. This is a positive 3. From a positive to a negative, that's one variation. So here's one variation here, from a positive to a negative. Negative to a negative, that's no variation. Negative to a positive, that's a variation. So that's 2. And then positive to a negative, that's 3. So you look for variations in sign, okay, to get that first box. Okay, to get the second box, okay, to get this one, everywhere you see an x in the original problem, you substitute in a negative x, and then you count variations in sign. So if we substitute in negative x in for the x, you'd have negative x, that quantity to the 4th, a negative to the 4th would be a positive, times a positive 3 would be positive. A negative x cubed would be a negative, times a negative 8 would be a positive. Negative x squared would be positive, times a negative 30 would be a negative. Okay, and then a negative times a positive 72 would be a negative. And there is no x to substitute into the negative 12, so it stays negative. And now you look for variations in sign. There's no variation from positive to positive. Positive to a negative, there's 1. There's no variation, no variation. So this is just 1. The 0 roots. Okay, to get this box, you look and see, this goes all the way back. I'll give you an example. If I had something like this, x squared minus 5x equals 0, what's in common there would be an x, and you'd factor it, you'd have x minus 5, and then x equals 0 would be 1 0 root, and x equals 5 would be the other root. But that's how you get a 0 root, is if you have a variable and x in common. Well, over here in the original problem, there is no x in common. So there are 0, zero roots. Another way to say that is, if there is a constant term in your problem, you won't have any zero roots because there won't be any variable in common. Okay, now this row across has to add up to the highest exponent. Okay, and it already does. So 3 plus 1 is 4, so the imaginary roots, you just figure out what would be left to add up to 4, and it would be 0. Okay, then we need to go back. This is one possibility, to have 3 positive roots, 1 negative root, 0 roots, and 0 imaginaries. If either one of these boxes, positive or negative, is greater than 2 or greater, I should say 2 or greater, then you can depress it by an even number and get another case, another possibility. So this number is 2 or greater, so you can depress it by 2, so subtract 2 from this, that'd go 1. If it's not 2 or greater, it's going to stay what it is, so this will stay a 1. And the 0 roots, that's going to stay 0. Now, what changes is the imaginaries. This row across still has to add up to that highest exponent, so that makes this go up to 2. So, we don't know what the answers to the equation are, but we know we either have 3 positive roots and 1 negative, or 1 positive root, 1 negative root, and 2 imaginary roots. Okay? Now, in the back of the book, the author is going to list these answers like with commas 3, 1, 0, 0, and, or 1, 1, 0, 2. I prefer that you keep it in a table, and we'll check it in table form. This whole method is called Descartes' rule of signs. Okay, it's named after a French mathematician, same one that did the Cartesian coordinate plane. It's called Descartes' rule of signs. It's probably pronounced Descartes, but I'm just gonna pronounce it Descartes. Descartes' rule of signs, and you make the table. Okay, let's look at another example. Same, it'll say use Descartes' rule of signs. Use Descartes' rule of signs to find the number of, and just abbreviate it, positive, negative, 0, and imaginary roots. Okay, and here's the beginning equation. W to the 4th plus W to the 3rd plus W squared plus W plus 3 equals 0. And we're going to do the table. It will always be, I don't know how many rows I need, but it will always be 4 columns, and it's always in this order: positive, negative, 0, and imaginary roots. Okay, so first, to get the positives, to get this box, everywhere you see an X, or a W, sorry, everywhere you see a W, you look for variations in sign. Okay, and there are no variations, so this would be 0. Okay, and then to get the next box, everywhere you see a W, you're going to substitute in a negative. So a negative W to the 4th would be positive. The negative W cubed would be negative. A negative W squared would be positive. And then this would stay a negative W and the positive 3. Okay, and count variations. There's 1, 2, 3, 4 variations in sign. To get the 0 roots, you look and see if there's a W in common all the way across, or another way to say that is if there's a constant term, there are no 0 roots. Okay, and this row across has to add up to the highest exponent. It already does, so this would be 0. If either this box, if the positives or the negatives, either one of those boxes is 2 or greater, you can depress it by an even number. Okay, so this would stay the same. This could go down to 2. The 0 root stays the same. and this row across has to add up to 4, so that takes this up to 2. Then this one can still go down, so this would stay a 0. This will depress it by an even number, so that means you subtract 2 from it, and then that means the imaginaries go up. So there are 3 possible cases for our answers. We either have 4 negative roots, or we have 2 negative roots and 2 imaginaries, or we have 4 imaginary roots. Okay? And we don't know what the case is without solving it. Okay? Okay, now the author's going to change the directions on this problem. Okay? Oh, before I go through that, let's go back through. If, separate this, if I had another problem in, let's say at my first row, I'm just making up one now. Let's say I had positive, negative, 0, and imaginary. Let's say my first row was a 5, and this was a 3. So let's say I'm ending up working an equation with an x to the 8th, okay? With an x to the 8th. So just to give you an idea, the bigger those first 2 numbers get, the more cases. These can go down together, or they can go down separately. So like I could subtract 2 from the 5 and get 3. This could stay the same, and it has to add up to 8. So that makes this have a 2. This could go down to 1. This could stay the same, and this could go up to 4. We've got several possibilities here. This could stay a 5. This could go down to 1, and then this would go up to 2. Let's see. Have we got them all? No, this could stay a 3. This could go down to 1, and then this could go up to 4. So you go through all the possibilities. The bigger these numbers get, the more possibilities. They can go down separately, or they can go down together. Okay? Okay. Now, let's go through another type of example. Okay, let's say they change the directions. Okay. Let's say they change the directions, and locate says, for example 3, locate between successive integers the real zeros of, okay, and our equation is f of x equals x to the 5th minus 7x minus 5. Locate between successive integers the real zeros of that function. Okay? Now, we're actually going to do this on the calculator and make tables, but what we're really looking for, when they say between successive integers, and I'm just making this up, they want to know, like, say I have a graph like this. They want to know, is it crossing between -1 and 0, between 1 and 2? Where is it crossing? Okay? Okay, first thing I would do is Descartes' rule of signs, because it will help tell us how many roots of each type we're looking for. Still do positive, negative, 0, and imaginary. Okay, the positive roots. How many variations in sign? From a positive to a negative, there's 1. Negative to a negative, no. So positive is 1. Everywhere you see an x, put in a negative x and look for variations. A negative x to the 5th would be negative. A negative x times a -7 would be positive. And then that stays a -5. So there's 2 variations in sign there. There are no 0 roots. Okay? And then this row across has to add up to 5. And it's already 3, so that means this is 2. If either one of these is 2 or greater, you can depress it by an even number. So this is going to stay 1. You can depress this by 2, and that means it goes up to 4. Now, how this helps us on our table when we're doing it on the calculator is, this says for sure we have one positive root. And then it tells us if we find one negative, this table tells us to keep looking because there are 2. Okay? You won't find the imaginary roots on the table. Okay? Okay, when you set up, and I do want you to write the table on your paper, on your graphing calculator, go to y equals, okay, and we want to put in the x, and then you can use that caret symbol, so it's going to look like this. In y sub 1, you're going to use x to the 5th, I call that a caret symbol, minus x to the 5th minus 7x, and then minus 5. You put that in the y sub 1, okay, minus 7x minus 5. That ought to be in the y sub 1. Now, right above the window key on the top row, do second function table set. Okay, and for right now, we're just going to look for the positive root. Okay, so we're going to do table start, and we're going to set the table start at 0. And then the delta, this symbol is the Greek letter delta, stands for change in. Delta table, the change in the table, we're going to count by ones. So, and let's start it down here a little bit. 0, 1, 2, 3, 4, and so on. Now, how do we know where our answer is going to be on the y? Well, if you go back for any graph, and I'm just making up one, if I have a graph and it crosses, you know, say I have a graph and it crosses between 0 and 1, then my y value had to go from a negative to a positive. If I cross over here, let's say between -1 and -2, then my y value had to go from like a negative to a positive. So I'm looking for changes in the y value. Okay, now you've got a delta table set up. Now go right above the graph key on the top row, do second function table. Okay, and you should see your table set up. 0, -5, 1, -11, 2, and 13. Okay, now there's a change in the y between -11 and 13. That means your graph had to cross between, okay, the graph had to cross between 1 and 2. Okay? So, when it says locate between successive integers, the real zeros, okay, and you want them in order left to right, so one of our answers is between 1 and 2. That's one answer. That's our positive root. So we've already found that one. Now we need to check for negatives. And actually, you could just use your up arrow. If you get your cursor on the 0 in your table and just use your up arrow, you'll find -1, 1. Okay, here's another. It crossed. The y value went from a -5 to 1. So it had to cross between -1 and 0. So there's another root. Now when you write this -1 and 0, think of it going left to right across your graph. So between -1 and 0. Don't write down between 0 and -1. Go left to right. Now that says we've found one of these. We need to keep looking. So on your calculator, go up arrow again, and it's -23. X is -2. So here's a change in the y value. So that means the graph had to cross between -2 and -1. Same thing, go left to right across the screen. So we found our 2 negative roots. We found our positive root. And if you go back and look at your graph, you can probably see on your calculator where it's crossing. You may even want to do change the window a little bit. Zoom decimal. You can kind of see on zoom decimal it's crossing between -2 and -1. It comes down, crosses up here, and then crosses between. So it crosses between -2 and -1, and crosses here between -2 and -1, crosses between -1 and 0, and then it crosses between 1 and 2. Okay, and you don't have to graph it unless they ask you to. We're doing this all by doing a table. Okay. Okay, now the author will take this one more step. Okay, and he will have you find out where it crosses to the nearest tenth. Okay, so change the directions. Find to the nearest tenth the real root, and we're going to find the one up here between 1 and 2. Find to the nearest tenth where it crosses between 1 and 2. Okay, so we're going to go back on your table. Go second function table set on your calculator. We still have the original equation in. Do second function table set. Okay, and we know it's going between 1 and 2, so we're going to put our first value at 1. The table start is going to be 1. The delta table, how we're counting, we're going to the nearest tenth. Okay, so set this to be 0.1. Okay, and then auto. Okay, and then above the graph key on the top row, do second function table. Okay, and now what we're looking for is where it's changing in sign. Okay, you should have like a -11, a -11.09 for 1.1, 1.2 is -10.91. They're all negatives. Keep going, scroll down on the Y. Okay, till you get down to here. 1.7 is -2.701, and 1.8 is 1.2957. There's a change in the Y value. It went from a negative to a positive, so that means it had to cross the x-axis. So our root is between 1.7 and 1.8. Now, the directions did not say find it between. It says actually find it to the nearest tenth. So now you have to decide, is it 1.7 or 1.8? The way you actually decide is if you have a root and it's crossing, okay, where it crosses, the Y value is 0. So to be able to decide, is it 1.7 or 1.8, you actually have to look at these two numbers and say which one of these two is closer to 0, because that's actually what our Y value is here. Okay, and the one that's closer to 0 is this one. So our answer is 1.8. Okay, so when you're looking for to the nearest tenth, you're actually looking at the Y value and pick the Y value that is closer to 0, and that will give you the answer, 1.8. Okay, so that's locating zeros between successive integers, locating zeros to the nearest tenth. Okay, the last thing the author does is the author talks about upper bounds and lower bounds. Okay, the author asks you to find what they call the least positive integral upper bound. Okay, and the greatest negative integral lower bound. Now we're going to do this a little bit differently than the author, and actually our method is going to be more exact than the author, and I'm going to show you what they mean by just looking at the graph. Okay, let's say I give you a graph and go out to, let's say, -4, and on the positive go out to 3. Okay, and let's say our graph starts down here, and let's have it cross between -4 and -3. Have it come down and cross between -2 and -1, and then have it come over and cross between 2 and 3. And I'm just making up a graph. Okay, now when they say a graph is bounded, okay, that graph is actually in an envelope. Okay, and the envelope would be this -4 and 3. This graph is not going to come and cross to the right of 3. Okay, so it's in that, and all of these numbers are bounds. All of these are upper bounds, but 3 is the least positive integral upper bound. Okay, then on the negative side, it's bounded. This graph is bounded by -8, -7, -6, -5, but -4, this graph is going down. It's not going to cross. It's not going to come up and cross to the left of -4. So it's like this graph is in that envelope. So the least negative integral bound is -4. Okay, and don't make it any harder than that. You graph it. You look at another way to say that is this graph is crossing to the left of 3. It's crossing to the right of -4. Okay. Okay.